Yasas Athena, imeo de Aronson o T-Rex tu Codosaurus, que petaxe ido meto catechidium o pterodactylo, yanasas matho nas cotonete metalagmenos. Alla, Fatocano sta Anglica. So what on infinite Earths makes mutation testing different from all the other software testing techniques? Mainly, most of the others are about checking whether or not our software is correct. But mutation testing assumes that our software is correct, at least in the sense of passing all its tests. Instead, mutation testing is looking at two other qualities. In a typical code base, in my opinion, the more important of the two is that our test suite is strict. Now you might be thinking, isn't that what test coverage is for? If we have 100% coverage, doesn't that mean that our test suite is strict and our code is fully tested? No. The only thing that test coverage tells us is that at least one test ran the code that it claims is covered, the stuff that shows up here in green. And conversely, that no tests ran the other code, what shows up there in red. It tells us nothing about whether the correctness of any particular piece of code had any effect on whether any test, let alone any particular test, passed or failed. And that's kind of what we mean when we ask whether a particular chunk of code is tested or not. So how can we tell if a particular piece of code is actually tested or not? As you may have guessed, that's where mutation testing comes in. To check that our test suite is strict, a mutation testing tool will try to find the gaps that let our code get away with unintended behavior. Once we find these gaps, we can fill them in by either adding more tests or by expanding existing tests. Lack of such strictness usually comes from lack of tests, of course, or poorly written tests, or poorly maintained tests, such as ones that didn't keep pace with changes in the code. And speaking of the code, the other thing that mutation testing checks for is that our code is meaningful, by which I mean that any tiny little semantic change, as opposed to structural or syntactic, will have a noticeable effect on the behavior of the code. Lack of meaning, or lack of meaningfulness if you're not into the whole brevity thing, comes mainly from code being unreachable or redundant or otherwise just not having any real effect. And once we find meaningless code, we can figure out why it's meaningless and maybe make it meaningful if that fits our purposes, but the usual fix is to just chop it out. Mutation testing puts these two together by checking that every tiny little change that the tool knows how to do does have a noticeable effect on the code's behavior, and that our test suite is strict enough to notice that change and fail. Now, not all the tests have to fail, but every change should make at least one test fail. Now, that's the basics of the positive side, but as Fred Brooks told us back in 1986, there's no silver bullet. Besides which, those are for taking care of werewolves, not mutants. The first drawback is that it's rather hard labor on the CPU, and therefore usually fairly slow. We certainly won't want to mutation test our entire code base every time we save a file. Fortunately, most of the tools come with ways to tell it, only bother checking this function, this module, this file, or whatever. Otherwise, it might take perhaps over a lunch break for a small system, maybe a weekend or longer for a larger one. Many of the tools also include various forms of incremental mode, such as only check what's changed since the last time we ran the tool, or the last git commit, or the change from the main branch. By combining these filters, maybe we could check the relevant changes every time we save a file, or at least mutation test our system over a much shorter break. Another drawback is that it's often not at all clear what we're supposed to do about the results. It tells us that some particular change to the code made no difference to the test results. But what does that even mean? It takes a lot of interpretation to figure out what a surviving mutant is trying to tell us. Their accent is very strange, and they're almost as incoherent as zombies, but with a much larger vocabulary, so they're not always on about brains. Worse yet, sometimes it's a false alarm, because a mutation might not make a test fail, but it might not make any difference in the behavior in the first place. But it can still take a lot of time and effort to figure that out. And even if a mutation does make a change, a lot of programs contain, actually most programs contain a lot of code that we just shouldn't bother to test, like debugging log traces. Fortunately, most of these tools have ways to tell it, don't bother checking this line, this file, this function, whatever. But that's usually done with comments, which can clutter up the code and make it a little harder to read. So now that we've seen some pros and cons, how does mutation testing work, unlike this guy? As Nechudan mentioned in his talk yesterday, in this very room, it mutates copies of our code, hence the name, and it does this with the intention to create test failures, otherwise known as faults. So mutation testing is categorized as a fault-based testing technique, and this means it's sort of related to something you might already be familiar with, Chaos Monkey from Netflix. But the way mutation testing works is sort of upside down from what mutation testing does. Chaos Monkey is best known for injecting faults, like excessive latency and jitter and dropped connections, into Netflix's production network. If all still goes well, in the sense that Netflix's customers don't notice and their metrics still look good, then Netflix knows that their error recovery is working fine. But mutation testing instead injects semantic changes, not necessarily problems. It doesn't know if these changes are all going to cause problems. We certainly hope they all will, but that's actually up to the test suite, which is kind of the point. It injects them into copies of our code, not our actual network, and it does its work in our test environment, not production. And if all still goes well, in the sense that our tests all still pass, that doesn't mean all is well. That means that there is a problem. Remember, each change should make at least one test fail. Mutation testing has also been compared to fuzzing, a security penetration technique involving throwing lots of random data at an application. Now, mutation testing is kind of sort of like fuzzing the code rather than fuzzing the data, but it's not random. But enough about differences. What exactly does mutation testing do and how? Let's start with a high-level view. First, our chosen tool breaks our code apart into pieces to test. Usually these will be our functions, or methods if we're using an object-oriented language, but I'm just going to say functions. Then for each function, it tries to find the tests that cover that function. If the tool can't find any applicable tests, then most of them will just skip this function, and better yet, most of those will warn us about it, so we know we need to go add some tests, maybe annotate them, more on that later. But some of them will use the whole test suite, which is horribly inefficient, because of course most of your tests aren't going to be applicable to this one specific function. Now, assuming we're not going to skip this function, the next thing the tool does is to make the mutants. And to do that, it looks closely at the function to see how it can be changed. And for each tiny little way the tool sees to change this function, it will make one mutant with that one tiny little change. In other words, that one mutation. Once our tool is done creating all the mutants it can from a given function, then it iterates over that list. And now we get to the heart of the concept. This chart represents the progress of our tool. Unfortunately, most of them don't give us quite all this information, let alone so neatly organized, but it's a conceptual model that I use to help illustrate the point. So for each mutant derived from a given function, the tool will run the function's tests, but it'll run them against the current mutant rather than the original function. If any test fails, this is called killing the mutant, and it's a good thing. It means that the code was meaningful enough that the tiny little change that the tool did in order to create this mutant, in other words, the mutation it injected, did indeed have a noticeable effect on the behavior of that code, and that our test suite was strict enough that at least one test would notice that difference and fail. Next, the tool will mark that mutant as killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it might make fail. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then this mutant is said to have survived. And that means it has the superpower of mimicry, skilled enough to fool our tests. Oops, I got a bit ahead of myself on the slides. Yeah, there we go. This usually means that our code was meaningless, or our tests were lax, or both. And now it's up to us to figure out how. Now let's peel back one layer of the onion and look at some technical details of how this works. First, our tool parses our code, usually into an abstract syntax tree. Some work a little differently, but the vast majority use an abstract syntax tree, so let's roll with that. So this code would become this AST, and I'm going to assume you're all familiar with the concept of an AST, or at least can figure it out from context, but don't worry about actually understanding this one in detail. Next, our tool will traverse that syntax tree, looking for subtrees, or branches, if you will, that represent our functions. And after finding them, it handles each one more or less as I described before, starting with finding the tests. But how does it do that? That usually relies on us developers either annotating our tests, as I hinted at earlier, or following some kind of naming convention. But these manual techniques are often supplemented and sometimes even replaced by the tool figuring out what tests call what functions, though that can sometimes get a little tricky and unreliable. After the tool has found the function's tests, then, assuming it's not going to skip this function because it didn't find any tests, it makes the mutants. And to make mutants from an AST subtree representing a function, it traverses that subtree just like it did to the whole thing. But now, instead of looking for even smaller subtrees to extract, like twigs or something, it's looking for nodes where it can change something. And for each one of those that it finds, for each way it knows how to change that node, it makes one copy of the AST subtree representing the function with just that one node changed in just that one way. For instance, suppose our tool has started traversing this AST function subtree, part of that larger AST I showed you earlier, and it's gotten down to this if condition. For each way it knows how to change that one node, it will make a fresh copy of this whole subtree with just that one node changed in that one way. And after it's done making all the mutants it can by changing that one node, then it would continue along to the next one and do likewise and so on until it has traversed the entire function subtree. Now, I've been talking a lot about changing things, so what kind of changes are we talking about? There are quite a lot. It could change a mathematical, logical, or bitwise operator from one to another. In languages and situations where that's allowed, it can also change it to one of the other categories. For instance, in many languages, we can treat practically anything as Booleans, and in some languages, we can treat anything as bit fields. So x times y could become x and y, or x bitwise exclusive or y. If the order of operands matters, it can swap them. It can change a comparison from one to another. It could insert or remove a mathematical, logical, or bitwise negation. It can remove a statement. It can remove an if condition so that something that might be skipped around or done is always done. Taking that one step further, it can remove a looping condition. So this something that might be skipped around, done multiple times, or done once is always done once. It could replace a function's entire contents with returning a constant, returning one of the arguments, raising a deliberate error, various other things, including nothing at all if the language permits. It could change a value to some other value, and for instance, changing 42 to any of these or many, many more, but I had to stop somewhere. It could even change it to something of a different and incompatible type, like changing a number to a, if I may quote Smeagol, string or nothing. There are many, many more types of changes, but I trust you get the idea. From here on, there are no more low-level details I want to add, so let's just peel back one more layer of the onion and look at some pseudocode that illustrates how this works. We're not going to stop to inspect this in detail, but if you haven't already grabbed the URL from the chat, the final slide also contains the URL for all the slides, so you can grab them and ponder this at your leisure. Now let's finally walk through some examples. And we'll start with a really easy one. Suppose we have a function like this. Never mind why, it just makes a good simple example. Think about what a mutant made from this function might return. Since that's what our tests would probably be looking at, it doesn't look like it would have any side effects. Mainly, such a mutant could return values such as any of these. And again, many more, but I had to stop somewhere. Now, suppose we had only one test like this. This is a rather poor test, and I think at least one reason why is pretty obvious to most of us. But even so, most of those mutants would get killed, the ones shown here in crossed out green. The ones returning constants are very unlikely to match. There's no particular reason the tool would put a 4 there, as opposed to 1, 0, -1, infinity minus infinity, the largest and smallest signed and unsigned integers, and so forth, and other significant numbers. Subtracting one argument from the other gets us 0, dividing them gets us 1, returning either one alone gets us 2, and the deliberate errors and mismatched types will at least make the tests not pass. But addition, multiplication, and reversing the arguments of the exponentiation will all get us the right answer. So mutants based on these mutations will survive our test. So how do we see this happening? When we run our tool, it should give us a report that will look kind of sort of roughly like this. The exact words, format, amount of context, and so on will vary enormously depending exactly which tool we're using. And there will be a list of tools later on. But the information semantically should be more or less the same, and to unpack that, what this is telling us is that if we changed the function called power, which is in demo.ex starting at line 42, in any of 4 ways, then all its tests would still pass. It then goes on to tell us that those 4 ways are to swap the function arguments, to change the exponentiation into addition or multiplication, or to swap the operands of the exponentiation. So what is this set of surviving mutants trying to tell us? We can tell from a glance at our code that it's probably not talking about redundant or unreachable code, because our function body is just 1 line, so that sort of problem is extremely unlikely. The main possibility that leaves is that we have a gap in our test suite. So the question boils down to, how are these mutants surviving? And the usual answer is that they return the same answer as the original function, or they have the same side effect, whatever it is that our tests are looking at. And to determine how that happens, it helps to take a look at one mutant and a test it passes. So let's start with the plus mutant. Looking at this change together with our test makes it pretty clear that this one is surviving because 2 plus 2 equals 2 to the 2 to 2 to 2 to 2 to 2. And so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run against the mutant that would pass when run against the original code. It's pretty simple in this case. We just need to make at least one test use inputs such that x to the y is different from x plus y. For instance, we could add a test or change our existing test to something like this, asserting that 2 to the 4th power is 16. All the mutants that our original test killed, this would still kill. But in addition, 2 plus 4 is 6, not 16, so this kills the plus mutant. See how that works? But wait, there's more. Better yet, 2 times 4 is 8, which is also not 16. We developers should certainly know our powers of 2 at least that well. So this kills the times mutant as well. Killing one mutant often kills other mutants of the same function in what Holly Cummins might call a double win. Though frequently, many more could easily be a quintuple or dozen win, depending how many mutants you still have for that function. Unfortunately, it's not a win-win in the sense of both sides winning, as the poor little mutants wind up getting killed, but it's still a multiple win usually for us. However, the pair of argument-swapping mutants still survive. Wait, how can that be? It's because with our new test inputs, these mutants return the same result as the original function, because 2 to the 4th equals 4 squared. But that's okay, we can attack them separately. No need to kill all the mutants in one shot and be some kind of superhero about it. To kill them, again, we can add a new test or adjust an existing test to maybe something like this, asserting that 2 cubed is 8. If we reverse those, so we get 3 squared, that's 9, not 8. So this kills the argument reversing mutants. Better yet, 2 plus 3 is 5, and 2 times 3 is 6, and both of those are, guess what? Not 8. So the plus and times mutants stay dead, and we don't get any zombie mutants wandering around, even if this were still our one and only test. With these inputs, the correct operation is the only simple common one that gets us the right answer. This isn't the only solution, though. Even if we stuck to single digits, there are lots of ways to skin that flurkin. This may make mutation testing sound simple, so let's look at a more complex example. Suppose we have a function to send a message, like so. Send message uses send bytes to send as many bytes as send bytes can send, kind of like a woodchuck, and loops to pick up where it left off until the message is all sent. A very common pattern, probably recognizable to any of you who've done communication software. Now, a mutation testing tool could make lots and lots of mutants from this, but one of particular interest would be this, an example of removing a looping control. Now, suppose that this mutant does indeed survive our test suite, which I'm not going to show you quite yet. But even without seeing the tests, what does the survival of this non-looping mutant tell us? If a mutant that only goes through that loop once acts the same as our regular code as far as our tests can tell, then our tests are only making our normal code go through that loop once. So what does that mean? Interpreting mutant often involves a lot of asking yourself, so what does that mean? Often deeply recursively. Good things humans seem to have tail call optimization. In this case, though, it means that we're not testing with a message larger than send bytes can handle in one chunk. And there's lots of ways that can happen, but I'm only going to look at two in this presentation, and the most likely is that we should have, but just didn't bother. For instance, suppose our maximum chunk size is 10,000 bytes, and yet for whatever reason, we're only testing with an itty-bitty 3-byte message. And the obvious fix in this case is to deliberately use a bigger message than our chunk size, and with this kind of messaging, that's very easy to do. Just take that maximum size, add some, create that bigger message. Done. But now let's look at a different possible cause and solution. Maybe we did test with the largest permissible message out of a predetermined set of messages, or at least message sizes. For instance, here we have small and large message sizes, and we tested with a large, and yet this mutant survives. What could possibly be wrong with that? I mean, it sounds good to me. What is this surviving mutant trying to tell us in this case? In this case, it's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, and then all the stuff that was only there to support the looping, we wind up with this. And now the ultimate message is much clearer, that the entire send message function may well be redundant, and we can just use send bytes directly. In real world code, maybe not. Maybe there's some logging, error handling, and whatever that we need in send message. But at the very least, the looping was redundant. Fortunately, when it's this kind of problem with redundant or unreachable code, the fix is clear and easy. Just rip out whatever it was that the mutant didn't have. This will also make our code more maintainable by getting rid of useless cruft that's just getting in the way of our understanding it. Now that we've seen a few different examples of spotting bad tests and redundant code, I'd like to address a couple of occasionally asked questions. Mutation testing is still rare enough that I don't think there really are any frequently asked questions. First, this whole idea sounds pretty weird, deliberately making tests fail to prove that the code succeeds. Where did this whole bizarro idea come from in the first place? Well, it turns out that mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper titled Fault Diagnosis of Computer Programs at Carnegie Mellon University. The first tool, however, didn't even appear until 1980 as part of Timothy Budd's PhD work at Yale. But even still, it was not yet practical on typical consumer or even developer-grade machines. That happened maybe around the 2000 or so, with advances in CPU speed, multi-core CPUs, larger, faster, cheaper memory, and so on. But that leads us to the next question. Why is it so CPU intensive? To answer that, we need to do some math, but don't worry, it's pretty basic. Suppose our functions have, on average, about 10 lines each, with about 5 places where it can be changed to any of about 20 alternatives. And that works out to about 1,000 mutants per function. And for each one, we'll have to run somewhere between one of that function's tests, if we get really lucky and kill the mutant on the first try, all the way up to all of that function's tests, if we kill the mutant on the last try, or of course it survives and escapes. Suppose we wind up running, on average, just 1/5 of the tests for each function. Since we start with 1,000 mutants, that's still 200 times the test runs as compared to just running our test suite. So if our test suite normally takes a zippy 10 seconds, then with these assumptions, mutation testing will take somewhere in the neighborhood of about 2,000 seconds. That might not sound like much because I'm saying seconds, but if you do the math, that's a bit over 33 minutes. Yes, well over half an hour. I don't know about you, but I don't want to sit there and wait for those test results. So to summarize at last, mutation testing is a powerful technique to ensure that our code is meaningful and our tests are strict. It's easy to get started with in terms of setting up the tools and maybe annotating our tests if need be. Yes, that's probably going to be tedious and time-consuming, but at least it should be easy. But it's not so easy to interpret the results, nor is it easy on the CPU. But even if these drawbacks mean that it's not necessarily a very good fit for our current projects at the moment, I still think it's just a really cool idea in a geeky kind of way. If you'd like to try mutation testing for yourself, here's a list of tools for some popular languages and platforms, and some other ones. I doubt many of you are doing Fortran 77 these days. And I know this is way too small for most of you to read, but once again, the chat and the final slide have the URL for all the slides, so you can grab this, copy into Google, whatever. But before we get to that, I'd like to give a shout out to TopTal, a consulting network I'm in, whose speakers network helped me prepare and practice previous productions of this presentation. Please use that referral link if you want to hire us or join us. The anchor part tells them it's me, and if you hire us or work a project through us, we both get some bounty. Yay. And now it's your turn. We have about 7 minutes for questions. Any questions? Okay, I'm not sure whether I've confused you too much for you to be able to formulate a question or I've explained everything perfectly clearly. I think I will assume the latter for the sake of my ego. Questions through the app, okay.
Attempting to practice mutation through manual testing, but any advice would be good.
Okay, the question boils down to, do I have any practical tips or experience for mutation with manual testing as opposed to our automated unit test suite and contract tests and so forth? I have not actually given that much given that point much thought off the cuff. Manual testing in the sense of being a user poking at a web app or a mobile app or whatever would not really be amenable to the sort of automation of mutation of it, but you could simulate that perhaps, break your app in various ways and still poke at it manually and see if it gives different results. But that sort of manual poking at it is so slow and error prone. That's why we do the non-manual kind. You're welcome. Anyone else?
Anyone else? We can. Right, I have a couple here on the app. Can mutation testing create a false positive, a mutation that passes all tests, and yet we should change the implementation all tests?
Did you hear that? I'll repeat it anyway. Long story short, can it produce a false positive? And yes, a fairly significant proportion of the surviving mutants will actually be false alarms of one sort or another. In particular, there are some squirrely edge cases where it would change perhaps a less than to a less than or equal to. A lot of tools won't do that because that's technically adding semantics, and a lot of them operate on a principle of semantic reduction or just staying the same level of complexity. But still, some will certainly do things like that, and you can wind up, or for that matter, the other way around, you can wind up with cases where, depending exactly what values you're comparing against, yes, moving the comparison from less than or equal to strictly less than or the other way around, or greater than, whatever, will yield one edge case that will still pass.
Thank you very much.
Yeah. And I think I saw a hand up right there.
Yes.
Okay. Yes, through the app. Good. Okay, anyone else?
Yes, right at the back over there. Yes, go ahead. There's no way we can hear you. Can you bring the microphone?
Or maybe if you type real fast, it might be faster to just type it in the app. I see he's got a mic with him now. Okay, great.
Actually, what I wanted to ask is how do you think this kind of testing is going to help an enterprise system to be able to test it and having good results on by applying this kind of method?
Okay.
The reason I'm asking is I'm more fond of BDD testing, behavior-driven development, because in this case you can understand the whole behavior of your system, especially if you have quite big business solution. Yes, a complex business thing. So how do you think this would add value to your system and these kind of things?
Okay, the question boils down to how would doing mutation testing add value to the development of an enterprise system, and in particular when they're already doing BDD and similar things. In the general case, the value of mutation testing is in finding gaps in the test suite and redundant and or unreachable or otherwise meaningless code. Now, BDD, which I generally consider just a high-level form of TDD, close enough, those things get you off to a really great start with a test suite. This is definitely not an either-or situation. But even doing things like BDD and TDD will not necessarily find all your edge cases, let alone your corner cases where the two edges meet and 3D corners and whatnot. Whereas mutation testing will help root those out. And there's not much that TDD or BDD can do about code that later becomes redundant or unreachable, whereas mutation testing will root those out as well by there not being any consequences to changing that code. So does that answer your question?
Yeah, sort of.
Okay, thank you. And we are at 40 minutes and a bit over 30 seconds, so I think we're done.
Dave Aronson, thank you so much.